Alright, so we're going to move on to look at the longer answer part of the end of unit test. The first one was about gravitational fields, and to start with we were looking at calculating the height above the surface of a satellite in a geosynchronous orbit. So geosynchronous is a geostationary. Key thing here is they're looking for the height, not the distance between their centres of mass. So in terms of solving this problem, it's about equating the equations of Newton's law of gravity and the centripetal acceleration or centripetal force equation as it ends up being. So first let's cancel out the masses, and now what we need to do is substitute in for the time period, because we know the time period of geostationary satellite is 24 hours. So then what we get is, let's speed things up, t squared times by r, and then if we rearrange this we can make r the subject. Let's again speed this up a little bit, keep it brute. G m, there shouldn't have been an m in there, t squared over 4 pi squared. So if you calculate that, you will end up with 4.2 times 10 to the 7 meters. But remember, this is the distance between the centers of mass, not the height. So the height is going to be the distance minus the radius of Earth, which is 6.37 times 10 to the 6. And what you get if you put that in, so you do 4.2 times 10 to the 7 minus 6.37 times 10 to the 6, and using unrounded versions you should end up with 3.59 times 10 to the power of 7 meters here, and it needs to be 3 significant figures because all of the information you'd have been using would have been 3 significant figures in terms of the radius of the Earth, in terms of g, and that kind of thing. Okay, so that's that one there. Moving on to the next question. The page. Wants to calculate the centripetal force acting on a polar orbiting satellite. Its mass is 650. So force is m when we get squared r equals m 4 pi squared r over t squared. Now the t is 105 minutes times by 60 to convert it into seconds. That all squared over 650 times 4 pi squared, and then we need to multiply that by the distance, so we can calculate that, and that's going to be 7.37 times 10 to 5. Sorry, times 10 to the 6, my mistake. And then once you calculate that, you end up with 4.8 times 10 to the 3. So the next question was the longer 6-mark answer question. I'm not going to be able to write it out on this tablet, but I'll look at some of the key points. Essentially, we're comparing the key properties of polar orbit satellite and a geosynchronous. So let's first look at this. So with a polar orbit, the satellite is going around this way over the poles. But because the Earth is rotating this way, actually the polar orbit satellite is able to look over all of the surface of the Earth during a few different time periods. It actually gets to see the surface of the Earth, whereas geostationary satellites, they have a time period of 24 hours, and actually they stay in a fixed position relative to the Earth. So that's one of the key differences. Polar orbits actually look down on all parts of the Earth. Geostationary is in a fixed position relative to the Earth, and that's one of the key points. So, in terms of how you use a polar satellite, it's used for mapping terrain, because you can actually look at very inaccessible parts of the Earth using it, because it covers the whole surface, and it updates more regularly, so it's quite good for weather, because if it's coming round and round several times a day, you can get regular updates on the weather. Whereas a geosynchronous satellite tends to be better for communications, because you just point your aerial or your satellite dish or whatever it is at a fixed point in the sky, and then you don't have to move it. Whereas for polar orbits, actually having satellite dishes, they have to be able to move and track across the sky, which is quite a disadvantage. So if we draw, if the essentially the geostationary will be going around like this, we can see the radius of this is quite considerably more than it is for the polar orbit. So actually your signal needs to be more powerful, or to use more energy to send a signal to a geostationary, because it's much further away, whereas polar is quite short, so it's a lower power type signal. So those were some of the key points to discuss. So just to quickly highlight what they were. So your first, well, one of the things to think about is signal tracking, which means that, so for geostationary, because it's at a fixed point in the sky, you can point your satellite dish straight at the satellite, whereas for a polar, you have to have some mechanism of making it track the satellite across the sky, so it has to be constantly moving. You also can talk about the signal power, so the fact that it takes more power to send to a geostationary because it's further away. You can talk about the distance here, and so in theory you could take higher resolution images from the polar because it's closer in, and the key thing that it actually covers the whole surface of the Earth, whereas a geostationary is at a fixed position orbiting around the equator.